Here we go, mathletes. 3.4 derivatives as rates of change. So we're going to talk about this. This is actually something we've talked about already, but we're going to talk about motion, and we're not going to cover everything in this section just for the sake of time, and there's some other things that definitely I feel are a little more urgent coming up. So coming up to the end of the term, we want to make sure we get some of those things in. So we're just going to focus on position and velocity and acceleration in this section. So all right, so all those things deal with motion, and so we've talked about this before, but S of t is usually the position function. Sometimes you'll see x of t, but yeah, S of t is what we'll be using, and so that's the position of an object at a certain given point in time, and t represents time. And so the velocity is the first derivative of position, right? So v of t, the velocity function, is equivalent to the first derivative of the position function. So it's the rate of change of position, right? That's what velocity is. Now, velocity is a vector, which means vectors have magnitude and direction. And this might be something you've learned in physics before. So vectors have magnitude and direction, right? They have value and they have a direction. And so scalars are the scalar is a counterpart that has magnitude only and no necessary direction. Okay, so speed is a scalar. So speed is the absolute value of velocity, right? So velocity tells you not only how fast you're going, but which direction you're traveling, right? Whereas speed just tells you how fast you're going. So I've used the analogy of like looking at the speedometer. So that doesn't really tell us where we're headed. So the velocity would be not only looking at the speedometer, but also looking at the direction that you're heading, right? So which direction you're heading. All right, and a lot of times the direction that we use for vectors, especially in calculus, are going to be just positive, negative. And so positive is going to be one direction, negative is going to be another direction. All right, and then the last thing here is acceleration. So acceleration is the derivative of velocity, right? So acceleration is the derivative of the velocity function, and it's also the second derivative of the position function, right? So acceleration is the rate of change of velocity. So how fast is the velocity changing over time is what the acceleration tells us. All right, let's compare instantaneous velocity and average velocity. We've kind of had this. We've mentioned this comparison or discussed this comparison before, but let's actually see at a certain value what the difference is. So we're given this function here, and this is projectile motion. So negative 16 t squared plus 64. So this is the projectile motion formula or model when you have negative 16 t squared. Negative 32 feet per second squared is the acceleration of gravity, and so in the formula you always have half of that before the t squared, and then 64 would be the initial height. And since it's dropped, that means the initial velocity is 0, and so that's why you don't see a value in there with the t next to it, because the initial velocity is 0 when you drop something. All right, so anyway, so that's our function. And so the first thing is we're asked to do here is find the instantaneous velocity of the ball when it hits the ground. So here's the path of the ball, right? This parabola represents that. It's a quadratic. So here's the starting point of the ball, 64, right? And then of course here's the ground. And so this ball has a path where it starts out when you drop it, and it speeds up, or the velocity or the absolute value of the velocity increases, right? until the point when it hits the ground. So the first thing, what is the instantaneous velocity of the ball when it hits the ground? So we're asking at 2 seconds, right? So we're basically saying the velocity at 2, right? And remember that velocity is the derivative of position. And so we really want the derivative of position at 2. So first, let's find the derivative of position. So here's the function. So the derivative would be, we can use the power rule here. 2 times negative 16 is negative 32. So it'll be negative 32t. The derivative of 64 is 0. And so this is our the derivative of position, which is also our velocity function. All right, so if I plug in 2, it'll be negative 32 times 2, and that gives me negative 64, right? And we're talking about feet per second, like we talked about. And so this will be 64 feet per second, negative 64 feet per second. Okay, so just to, even though they're not asking this, if I asked you what the speed was, or if we were asked to find the speed, it would be positive 64, right? Because it's always the absolute value of velocity, right? So speed doesn't have a direction, but velocity does, right? This negative means we're heading down, right? We're heading down, and so that's why we have a negative velocity. Okay. All right, and then the second thing is we're asked to find the average velocity during the fall. So average velocity, remember, is we're just starting at the endpoints if we want the entire fall, and we're trying to find basically that slope right there, right? And so remember, average rate of change is f of b minus f of a all over b minus a. Okay, so this is the average rate of change formula. And so f of b, so that's where we ended up, right? That's our output where we ended up, and that's 0. So it'd be 0 minus where we started, f of a, which is 64. Okay, and then the bottom, b minus a. So this is, once again, where we ended up. That's the input value is 2 minus the original input value is 0. So it's negative 64 over 2, which is negative 32 feet per second. Okay, so the instantaneous velocity was negative 64, whereas the average velocity was negative 32 feet per second. All right, so you can see that, for a function that's starting to go faster and faster and faster in terms of speed, the point where it almost hits the ground is going to be the fastest point, right? And so the average is, of course, not going to be that fast because we're taking into account where we started, which was 0 velocity, all the way to when we ended up, right? And so, so that just gives you a sense of, just the difference between instantaneous and average velocity.